Hi everybody, this is the second part of our lecture on Chapter 2 on predicate logic. Um, so let's hop right into an example for translating English language statements into predicate logic statements. So last time we looked at statements that just used one quantifier. Now we're going to look at statements that are going to require more than one, two quantifiers typically. And let's recall the two main principles that we have been talking about in doing this. The first principle is whenever universally quantifying a subset of the domain identified by P of x, we write for all x, P of x implies. So all ponies eat grass, all ponies run fast, no ponies are green, something like that. Okay? Never write for all x, P of x, and. Such a statement is always false because, the whole domain, the domain is typically the whole world. Not everything in the domain is P, identified by P, a pony. Or like P of x maybe means x is a potato, right? All potatoes are brown, all potatoes grow underground, all potatoes, taste like candy, whatever it might be. It's never all potatoes and, right? That's just going to be false because there's going to be a lot of things in the universe that just aren't potatoes. Whenever existentially quantifying over a subset of the domain identified by P, all potatoes are, there is a potato, there is a pony, something like that, some ponies, right? There exists x, P of x, and. There is a pony that's brown. There is a pony that runs fast. There is a pony that's purple. Okay, there is no pony that's purple. Never write there exists x, P of x implies, because that's always true. Pick something in the domain, the entire universe, that's not a pony. So one thing in the domain that's not a pony. So there exists x in the domain that makes P of x false. Therefore, there exists x in the domain that makes the implication true. Okay, so that's not how you ever want to translate anything. That's just got a default truth statement. All right. So, a two quantifier example. So let's say f of x equals x is a farmer, y of x is yellow, v of x is x is a vegetable, and gxy, so a two variable predicate is x grows y. Okay. A. All farmers grow some kind of vegetable. Right? All farmers grow some kind of vegetable. So the statement is all farmers. All farmers do something. Okay, so we're universally the domain. Domain is the whole universe. So we're universally quantifying a subset of the whole universe, subset of the domain, that is all farmers. So all farmers grow some kind of vegetable. So for all x, f of x implies all farmers do something. All farmers wear overalls, all farmers have a tractor, all farmers have land, all farmers grow some kind of vegetable. Okay, so all farmers grow some kind of vegetables. So there exists X, or not X, sorry, there exists Y, okay, that is a vegetable, and this farmer X grows it. G, X, Y. Okay, so for all X, if X is a farmer, then there exists a Y that is a vegetable, and the farmer grows the vegetable. Right? That's for all X in the universe. If X is not a farmer, then this is automatically true. Okay? So all farmers grow some kind of vegetable. Supposing that statement is true, that all farmers do grow some vegetable, then clearly this one is true, as we've been saying. Anything in the universe that you pick that's a farmer, if it's not a farmer, the implication is automatically true. For every X in the universe that you pick, if X is a farmer, then, since this statement is true, there exists a Y, like for Farmer Xavier, Y is asparagus. Asparagus is a vegetable, and he grows it. Okay? If it's false, right, all farmers, it's not true that all farmers grow some kind of vegetable. That means there is a farmer that doesn't grow any vegetables. Right? He just raises cows. Okay? Or, gets milk for cows or eggs from chickens. Right? So some farmers just don't grow any kinds of vegetables. So you pick that farmer, Farmer Xavier. Farmer Xavier has a chicken farm where he does chickens and eggs. And, so there's no veggies on that farm that he's growing. So this is false. He's a farmer, true, but there does not exist a vegetable that he grows. This can also be written as follows. It doesn't read the same way in English, but logically it's equivalent. And uses fewer parentheses. For every X, there exists a Y. If X is a farmer, then Y is a vegetable and X grows Y. So it can be written like that, although the statement kind of reads, the English translates more directly this way, it's logically equivalent to that. All right. Oops. B. Some farmers don't grow vegetables. Some farmers don't grow vegetables. Okay, well, some farmers. There exists X, that's a farmer, and what about him? He doesn't grow vegetables. How are vegetables quantified? Some farmers don't grow some vegetables. Is that what we're saying? Some farmers don't grow some vegetables. Or are we saying some farmers don't grow any kind of vegetable at all? The second thing, some farmers don't grow any kind of vegetables at all. So there exists X such that X is a farmer, and for every Y, so we're quantifying vegetables universally. So if it's a vegetable, then he doesn't grow it. Okay, could also be written like this. There exists X such that for every Y, there exists an X for every Y such that X is a farmer, and you need the parentheses here in this case. If it's a vegetable, then this farmer doesn't grow it. So some farmers don't grow any kinds of vegetables. Okay. C. No farmer grows vegetables. No No farmer grows vegetables. None at all. None at all. Okay. No farmers grow vegetables. How can you say it without the no in the subject? Right? When you say no farmer, that's universally quantifying farmers. Right? No farmers, no farmers own cows, or no farmers, no farmers live in downtown Dayton. Right? No farmers live in downtown Dayton. That means what? All farmers don't live in downtown Dayton, or all farmers don't grow vegetables. Okay, means right, all farmers don't grow vegetables. Okay, whenever you say no farmer, or whenever you have that no in the subject like that, that's universal quantification, right? No ponies are purple. No ponies are purple. What do you mean? You mean that all ponies are not purple. Okay? Okay, all farmers don't grow vegetables. All farmers is this. All farmers do something. Okay, what is it this farmer does? He does not grow vegetables. What kind of vegetables? All of them or some of them? All of them. Okay, so for all y, if it's a vegetable, he doesn't grow it. Now this statement, so all farmers don't grow any kind of vegetable. This statement can be written in several different ways. Again, you can pull this quantifier out front, and it still makes sense from a predicate logic point of view. Farmer X implies vegetable Y implies not growing it. Okay, but remember the exportation tautology. The exportation tautology was that P implies Q implies R is logically equivalent to P and Q implies R. So this is actually the same as for all X, for all Y. X is a farmer and Y is a vegetable implies not growing it. So a few different ways you can write that statement. By the way, I always said don't use conjunction with universal quantification, but we're using conjunction to make the subject more, to take into account a two-variable subject. The subject in this, for every pair, X a vegetable, Y a farmer, X doesn't grow Y. For every pair of X and Y, where X is a farmer and Y is a vegetable, it implies that X doesn't grow Y, because no farmers grow vegetables. Okay? Only farmers grow vegetables. Only farmers grow vegetables. This one's a little tricky, this only construction. Only farmers grow vegetables. Okay. How does this only thing work? Maybe let's take a simpler one before we do this. All vegetables are yellow. Right? That was I said C. I think this is D. All vegetables are yellow. So it's just a single variable thing. All vegetables are yellow. For all x, vegetable x implies yellow x. All vegetables are yellow. E. Only vegetables are yellow. Only vegetables are yellow. Nothing else, just vegetables. Not corn. Corn isn't yellow. Right? Your house is not yellow. Right? Your car is not yellow. Right? The traffic light, middle light, it's not yellow. Okay, only vegetables are yellow. What's being quantified? Something's quantified universally, but it's not vegetables. It's not vegetables. Only vegetables are yellow. Can you say it as an if-then statement? The if-then statement is not if it's a vegetable, then it's yellow. It doesn't say all vegetables are yellow. It says only vegetables are yellow. It doesn't leave out the possibility that some vegetables are green. Only vegetables are yellow. What's being quantified universally are yellow things. Right? If it's yellow, then it's a vegetable. If it's yellow, then it's a vegetable. Or if it's not a vegetable, it's not yellow. Right? So if it's yellow, then it's a vegetable. So it sort of flips around the hypothesis and the conclusion. It sort of flips around the hypothesis and conclusion. By the way, another way you can say it is only vegetables are yellow. Only vegetables are yellow. It's saying that yellow things are a subset of vegetable things. Only vegetables are yellow. Yellow things are a subset of vegetable things. So, we know that containment relation kind of, that it describes a implication. Right? Defines an implication. All right. So back to the farmers. Only farmers grow vegetables. So it's vegetable growers. If it's a vegetable grower, right, then it's a farmer. Right? If it grows vegetables, then it's a farmer. Only farmers grow vegetables. So if it's a vegetable grower, then it's a farmer. Or, right, so veggie growers. So G, X, Y, and veggie Y implies farmer. Or if it's not a farmer, then it doesn't grow vegetables. I think maybe this one is easier. Just not the contrapositive. For every X and for every Y. If X grows Y, and Y is a vegetable, then X is a farmer. If it grows vegetables, then it's a farmer. Right? Only vegetables are yellow. If it's yellow, then it's a veggie. Okay? All right. Take a break. Okay. Next topic will be on interpretations. So, given an abstract predicate logic statement, such as something like this, for all x, hx implies mx, and there exists x, hx implies there exists x, mx. An interpretation of such a statement is, one, a choice of domain. Any domain, doesn't have to be the whole universe. A choice of domain, and two, meanings assigned to the predicates. So, something like this. Oh, let me change it a little bit. So, interpretation number one. For this statement up here. So, let's say domain is all positive integers, 1, 2, 3, 4, 5, something like that, all positive integers. H of x means x is even, and m of x means x over 2 is an integer. In this case, in this interpretation, so that's a domain, and these are meanings for the predicates. Notice the meanings for the predicates are full sentences that use x. Okay? So there's a subject, verb, and, second part of the sentence. So the subject, verb, and it's called a predicate, unfortunately. Subject, verb, and the description, I guess. At the very least, that's what a sentence has. So in this interpretation, notice that for all x, hx implies mx is true. For every x in the domain of natural numbers, if x is even, then x over 2 is an integer. It's more or less the definition of even, right? And there exists x, mx. Right? There exists in the domain x such that x is even. That's true as well. Therefore, the hypothesis itself of this implication here, the conjunction true and true, is true. But for all x, mx, right, for every x in the domain, x over 2 is an integer. Now 3 over 2, 5 over 2, 7 over 2, right, those are not integers. Odd numbers when you divide them by 2 aren't integers, so that's false. So we have true implies false, so the statement is false in this interpretation. The statement is false in this interpretation. So we have this abstract statement. I mean, we don't have that h means something, m means something, and we don't have a domain. It's just quantifiers and symbols for predicates. Okay, when we interpret it, we assign a domain and meanings for the predicates. Where do you get them from? You pick them off the top of your head. Okay? Just made them up. Okay, now, the point in doing that typically is to find an interpretation where it's false. We might also, that's the important part, we might also want to find an interpretation in which it is true. Interpretation number 2. For that same statement. So in this interpretation that I gave here, the statement was false. Let's make one where it's true. And I'm not going to fuss about it too much. I'm just going to make an interpretation where this is always true. This is true right here. M of x is always true. I'm not even going to give a meaning for h. Right? So the domain, I'm going to make, again, positive integers. H of x, I don't care what it means. And then M of x, x is a number. Okay, so in this interpretation, right, for all x, M of x is true. So the implication, the whole implication there is true. Is also true. So I have an interpretation where that abstract statement is true, and an interpretation where the abstract statement is false. Okay, typically you're more interested in the one where it's false. Okay, because that shows that an abstract predicate logic statement is not what's known as valid. So, while abstract predicate logic statements are true or false depending on the interpretation, an abstract most, I guess. An abstract predicate logic statement is said to be valid when it's true over any interpretation. No matter what interpretation you give it, it's going to be true. And the two important examples are, well, here's an example, although it's not really an important one. And it's just like this one, very close to it. That one isn't valid. Right? This is not valid. Because it's got an interpretation where it's false. We gave one. Okay. If I change the for all here to there exists, then it is valid. I mean, showing that it's valid, well, there are methods for doing so, but we're not really going to go over that. It's not a course in, in symbolic logic, so we're not really going to go over like general tools for proving it. But this basically says the following, right? Assuming the hypothesis, we don't care if the hypothesis is false. Okay, if the hypothesis is false, then the implication is true. So, assuming the hypothesis is true, that Hx, things that are H, are contained within things that are M. H's are contained within M, and there exists something inside H, right here. There's somebody inside H, call him P. Therefore, there is something inside M, because M is containing H. Because that guy P that's in H is also in M. So, kind of the way this one goes, like when you when you take symbolic logic for the first time, they kind of say, here's sort of a general interpretation of what this seems like, right? All humans are mortal. All humans are mortal. And someone is human. Therefore, someone is mortal. That kind of thing. I'll put this picture right here. All right. However, another example, which is more important than that, are De Morgan's laws for predicate logic. And De Morgan's laws for predicate logic deal with negations. For all x, p of x negated. So we talked about, negating propositional logic. But in predicate logic, it requires dealing with negations of quantifiers. And we talked about it a little bit, but here we're going to make it a little more formal. If you want to negate the statement for all x, p of x, it's logically equivalent to there exists x that's not satisfying p. Right? Everything is a pizza. Everything is a pizza. That's not true when something is not a pizza. Right? Everything is a pony. It's not true when something is not a pony. Something is not a pony is true when everything is a pony is false. And then the other way around, if you want to negate an existential statement, it's not true that something is a unicorn. Something is a unicorn is not true when everything is not a unicorn. Everything is not a unicorn means there's no such thing as unicorns, right? So that's De Morgan's laws for predicate logic, essentially because a universal quantification is kind of like doing a conjunction over the entire domain. When you're doing a conjunction over the entire domain, you negate it, you're doing a disjunction over the entire domain, right? Like A1 and A2 and A3, and A n not, like a big old conjunction. You want to negate it. That's logically equivalent to A1 not, or A2 not, or A3 not, or AN not. So if you're doing an infinite conjunction, it's like doing an infinite disjunction of the negatives. Disjunction is like there exists, right? This is, not a unicorn, or this is not a unicorn, or this is not a unicorn, or there exists means we're looking for one that's true. Right? There exists means you're looking for one that's true. For all means you're looking for all of them to be true. So that's conjunction, that's disjunction. So kind of generalizations of conjunction and disjunction. These quantifiers. Okay, so we can use De Morgan's laws for negating statements. One, all horses are brown. My favorite one. All horses are brown. Negated is, right? Some horses are not brown. Right? A horse of a different color. The proverbial horse of a different color. All. I like it because my dad used to say that to me a lot. Now, that's a horse of a different color. All horses run fast and eat grass. All horses run fast and eat grass. Okay, so negate the quantifier, all horses, right? Some horses, or there is a horse. Some horses, or there is a horse. Some horses don't run fast and eat grass. So we got to negate the conjunction. Don't run fast and eat grass. We're not going to say don't run fast and eat grass, right? Or run fast and eat grass, not. That means some horses aren't fast, either aren't fast, or don't eat grass. Some horses either aren't fast or don't eat grass, right? Running fast and eating grass. Not, right? That's De Morgan as well, right? Is not fast or not eating grass. Right? Three. Some horses race at the track rather than pulling wagons. Right? So some horses race at the track rather than pulling wagons. Let's sort of untangle that a little bit. Right? Some horses race at the track rather than pull wagons or pull. Right? Can be said as, right? When you say rather than, what does that mean? That's a conjunction, right? That's a conjunction, rather than. Like, I ate fish rather than chicken tonight. I ate fish rather than chicken tonight. Means I ate fish and I didn't eat chicken. That's what the rather than is, right? We have, so P rather than Q means P and not Q. Another example of a conjunction. So some horses race at the track and don't pull wagons. So now let's negate it. Right? Negated is what? Some horses negated. So first you negate the quantifier. First negate the quantifier. Some horses. Okay, all horses. All horses what? Now negate this. Race at the track and don't pull wagons. All horses either, right, that's an and, right, race at the track and don't pull wagons. And we're going to negate that, right, so that's going to be don't race at the track or pull wagons. Right, so some horses either don't race at the track or pull wagons. Oops, I shouldn't have erased that. Some horses don't race either. Don't race at the track or pull wagons. Or all horses, every horse. Let's do it in a singular voice. Not every. Every horse. Right, all horses, right, is a plural kind of thing. Like all horses, all horses eat grass. Right? But you could also say it in a singular way, even though it's universal. Every one horse, either doesn't race at the track either doesn't race at the track or pulls wagons. All right. Right. So we'll do more examples of these in class, but I would like to end the presentation on this section at this point. And how long is this? 40 minutes. Okay. All right. So that's the end of the lecture on Chapter 2.